Hi, today this video is about example for compressor. And so first thing we do when we solve open system device, we go ahead and draw. So if this is a compressor, it's going to from enlarged end to a narrowed end. So that's a compressor. So this is inlet and it come out at the narrow end. In order to do so, we have to have work coming in, right? To compress and to increase the energy of the fluid. And be aware this is nitrogen, not air. So we're going to make sure the table we're using is correct. And they said initial pressure is 0.1 megapascal. That's where we put it. That's inlet and 25 degree. And compress, the temperature becomes 125 degree Celsius. And the mass flow rate for this is 0.2 kilogram per second. Then we need to find out the work done. So in kilowatt, so basically it's determine the work done on the nitrogen. So basically they ask you what's going to be the required work coming in. That's the question mark we are solving right here. Okay, so compressor, we're going to go to the governing equation directly. For compressor, so it's work coming divided by time with a dot, right? That's going to be equal to mass flow rate H2 final minus initial, H2 minus H1. Because you require work increase the mechanical energy of the fluid, so H2 is going to be greater than H1. So here's the equation then. If we understand everything, this problem is really straightforward because they are asking this work come in, which is mass flow rate is given 0.2 kilogram per second. And H2 minus H1, that's a topic for finding, let me use a different color. That means H2 minus H1, that's delta H for nitrogen. That means delta H for ideal gas. And we're talking about this has so many different methods. There are three methods, right? The first method is using H2 minus H1 using the correct ideal gas table. The second one, we're going to just using CP at average temperature and then T2 minus T1. The third one will be our CP at this 300 Kelvin, T2 minus T1. Okay, so those are the three different methods. And then we have to decide which one are we going to use here. And since they do give us these two temperatures, we can go ahead using method 1 or method 2. I mean, that would be pretty accurate. You can potentially use 300 Kelvin as well, but we can just go ahead and use those two methods. And here I'm going to use the second method, okay? So knowing that now, we can go back to work on our H2 minus H1, work on here. So we're going to use CP at our average temperature. Our average temperature will be half 25 degree plus our 125 degree. That will give us 75 degrees Celsius, right? And so 75 Celsius, we might need to change that to Kelvin. So we plus 273, that will give us 348 Kelvin. So that's going to be at 348 Kelvin. And then T2 minus T1. T2 is going to be 125 minus 25. Okay, so even though that's both in degree, but we know this actually can be used for Kelvin because degree change in degree Celsius is delta T in Kelvin. So knowing that, we can go ahead and solve our work in power. So it's 0.2 kilogram per second, that's our mass flow rate, times our CP at 348. So where do we get that information? 348 is pretty close to 300, right? But, well, let's go ahead to see our table. So that's going to be our nitrogen. If we're using 300 for nitrogen, let's go down the list. That will be using this one right here, 1.039, right? Okay, we can potentially use that. Let's see if we were trying to use this, if there's a nitrogen table, which they do, and our average temperature is 348, which is really close to 350. So that would be better than 300, right? So go cross, our CP is about this value. So we can go ahead and use that one, 1.041. 1.041. And that will be in units of kilojoule per kilogram per Kelvin. And then times the temperature difference, 125 minus 25, that gives us 120 Kelvin. Then Kelvin cancel out, kilogram cancel out. Then we would get our unit of kilojoule per second. Okay, so calculate that. That will give us answer of 20. Let's take a look. 1.041 times 0.2. That will give us 20.82. And what's the unit for kilojoule per second? Joule per second, energy divided by time, that's our power. So it's basically 28.2 kilowatt. So that's how much power required for this compressor to increase the pressure temperature from 25 degrees to 125 degrees Celsius. So that wrap up the example for compressor. So I'll see you next time. Bye.